In this presentation, I'm going to explain dual converter fed DC motor drive. This is used for 4-quadrant operation of DC motor drives. Dual converter, or that's also called 4-quadrant converter. Now coming to this diagram here, this is a single phase half control converter fed separately excited DC motor drive, in which we are using a single phase supply and half control rectifier is used, in which you can see that one leg is 2 diodes, another leg is 2 SCRs, and by controlling the firing angle of this SCR, you can vary the voltage across the armature. That is given by, it is equal to Vm by pi into 1 plus cos alpha. If you change the firing angle from alpha 0 to pi, always you will be getting, when it is 0 it is equal to Vm by pi, and when it is equal to pi it is equal to 0, or when it is equal to say pi by 2, you will be getting it is equal to Vm by pi. That is, always you will be getting a positive voltage across the armature. Therefore, and the current is also always positive, because this device can conduct only the current in the direction. Therefore, it can operate with a positive voltage, and positive current, or it can operate in a first quadrant. Now coming to the second one, this is called fully controlled single phase fully controlled rectifier fed DC motor. In this case, the average voltage across the armature is given by equal to 2 Vm by pi cos alpha. Therefore, as alpha is equal to, as alpha changes, if alpha is less than pi by 2, you will be getting a positive voltage. If alpha is more than pi by 2, you will be getting a negative voltage. You can have either positive voltage or a negative voltage. But the current is always towards A1 to A2, because this is a unidirectional device. Therefore, you can have either first quadrant operation or fourth quadrant operation by a single phase fully controlled rectifier. Now this is similar thing for a 3-phase also. If 3-phase half control rectifier, that's also can be operated. It is a first quadrant, and if the 3-phase fully controlled rectifier for DC motor, it can operate either in first or fourth quadrant. Now dual converter can operate in all the 4 quadrants. That is, you can have output voltage either positive or negative. Similarly, the current through the motor can be either positive or negative. Therefore, this is the 4-quadrant operation, in which this is equal to a positive voltage and positive current. That is called the forward motoring. And you can have a positive voltage and a negative current. That is called the reverse regeneration. And here you have a negative voltage as well as negative current. The product is a positive. Therefore, it's a motoring action. In that one, this is called the reverse motoring region, or that quadrant. And in this case, it is equal to the current is equal to positive and voltage is negative. Therefore, the power is equal to negative. Therefore, it is equal to, and similarly, if you see that one, the omega m is equal to negative. That is why it's called the reverse regeneration. Therefore, this is a plot. This is a plot representing the 4-quadrant of operation. Axis will be in electrical thing. It will be the current axis and voltage axis, and in mechanical plane, this will be this will be the torque axis, and this will be the omega m axis. Therefore, 4-quadrant operation dual converter can be operated. Coming to the circuit topology of a dual converter for DC motor, in which dual converter consists of 2 fully controlled rectifiers connected in anti-parallel across the armature. Across the armature, 2 fully controlled rectifiers, they are connected in anti-parallel. This can be either single phase or 3-phase. That is, that depends upon the power rating. So if it is less than 10 kW, we'll be using a single phase fully controlled rectifier, and if it is more than 10 kW, we'll be using a 3-phase fully controlled rectifiers. That is, for power rating up to 10 kW, a 3-phase or single phase fully controlled rectifier can be used, and for higher range, we can use a fully controlled rectifier can be used. Therefore, the 2 rectifiers, they are connected in anti-parallel across the armature, and by controlling these rectifiers, you can get either positive voltage or negative voltage across the armature. Similarly, you can have a positive current or a negative current through the armature, so that this motor can be operated in all these 4 quadrants. Coming to the circuit topology of a dual converter, and here there are 2 rectifiers, that is named as rectifier A and rectifier B, and the rectifier A can provide a positive motor current, and a voltage can be either positive when alpha is less than 90 degree, or it is negative when alpha is more than 90. That is, when alpha A is less than 90 degree, you will be getting a positive voltage. When alpha A is more than 90, you will be getting a negative voltage. But always it can drive a current in this direction. Positive current only it can drive. Motor can be controlled by using this one. You can make either positive voltage or negative voltage. Always the current is positive. That is why it can be operated in either in first quadrant or fourth quadrant. Now motor can be operated in quadrant 1 or quadrant 4. Now the rectifier B, the second rectifier, this rectifier B can provide negative motor current, because the current is always in this direction. Therefore, from that is A1 have to be A2 to A1. The current is opposite to previous one. Therefore, it can provide a negative current through the armature or through the motor, and the voltage can be either positive or a negative. That is, here when alpha is less than 90 degree, it will be positive, or more than it is equal to 90 degree. So that you can bring the voltage either positive or negative across this one, and you can make the current always negative. Therefore, by this one, it can be made to work either in second quadrant or in third quadrant, in second quadrant or third quadrant by this rectifier B. And this one, there are two methods of control of this dual converter. And the first method is called circulating current type. That's also called simultaneous type. In that one, both converters are controlled simultaneously. There will be a circulating current. It's called a circulating type. Second one we call it as non-circulating current type. In that one, it is only one of the converter will be controlled at a time, and there's no circulating current. That's the second method of control of dual converter. Anyway, dual converter can be used to have a 4-quadrant operation of a DC motor. Now let us see circulating current type of dual converter. Also, that is called simultaneous mode. It is called. For the two converters, converter A and converter B, they are connected anti-parallel across the armature, and there's the inductors are linked. The inductors are the that will be controlling the the circulating current, and 3-phase supply is given to both rectifiers. And in simultaneous control, both the rectifiers are controlled together. Both are controlled at the same time. For in order to avoid the DC circulating current between these two rectifiers, they are operated to produce same DC voltage across the motor terminals. In order to avoid DC circulating current through this one, what we are doing, they are operated to have a same DC voltage. For average voltage, VA average voltage is same as average voltage BA. In such a way, in that case, there won't be any DC current flowing through the loop. But although the DC current is 0 here, if you see the instantaneous current through this one, that will be not equal. Therefore, although the current, the control of firing angle as per the this relation prevents, that is, the relation is that VA plus VB equal to 0. That's the average voltage across the this one rectifier A plus VB, that should be equal to 0. Then only you can the DC current through this can be brought to 0. Or substituting that one, 3 VML by pi cos alpha A plus 3 VML by pi cos alpha B equal to 0, or cos alpha A plus cos alpha B equal to 0, or alpha A plus alpha B should be equal to 180. About the sum of the firing angle of rectifier A and B, that should be equal to 180, or alpha B equal to 180 minus alpha A. This should be obeyed in the case of circulating current mode of control of dual converter. Then only you can make the DC current flowing through this loop to 0. Now, although the control of the firing angle as per this relation, that is alpha A plus alpha B equal to 180, DC circulating current, you can reduce the DC circulating current to 0. But AC current does circulate due to the difference between the instantaneous output voltage. If you see the instantaneous output voltage, this is the instantaneous output voltage across this rectifier. The second one is the instantaneous output voltage, this second rectifier. Now, if you take that one, instantaneous voltages are not equal, and due to the difference in instantaneous voltage that is across the output of this rectifier, that since they are not equal, that will be causing a circulating current through the through this loop. Therefore, there will be due to this difference between the instantaneous output voltage of the two rectifiers, there will be a circulating current, and to limit this current, To limit the current to the rectified, inductors are provided. L1 and L2 are added to reduce the circulating current. Therefore, since the instantaneous value of the AC currents are not equal, there will be a circulating current through this loop. And to limit that circulating current, we are providing the inductors L1 and L2 in simultaneous mode of controlling of dual converter. Coming to circulating current type of dual converter, simultaneous mode. In this case, both converters are conducting simultaneously. When operating in quadrant 1, that is, you are getting a rectifier A will be the firing angle A will be between 0 and 90 degree, and rectifier B will be in inverting mode. Alpha B will be between 90 degree and 180 degree. Therefore, to operate this one in the first quadrant, this is the condition. Now to reverse that motor, that is, this is mean forward motoring. In order to bring into the reverse motoring operation in the third quadrant, cannot directly brought to this one. And here also, when you are working in a forward motoring operation, alpha A plus alpha B should be equal to 180. Sum of the firing angle should be equal to 180 degree. Now, the magnitude of back EMF, that is, if you increase, what happens to reduce the, to make it to operate in this third quadrant, first it is brought in the second quadrant. To bring the second quadrant, we are, for speed reversal, alpha A is increased and alpha B is decreased, satisfying alpha A plus alpha B equal to 180 degree. And then since alpha A is increased here, the voltage get reduced, and then what the back EMF will become more than the average voltage, so that the current direction through the motor gets reversed. That will be working in, that is, I will be reversed, that will be working in the second quadrant. Now the magnitude of the back EMF exceeds VA and VB, and the armature current shifts to rectifier B, and the motor operates in the quadrant 2. Now the firing angle of the rectifier B, alpha B, is adjusted to break the motor and then to accelerate in the reverse direction. That is made to work in the third quadrant, that is reverse motoring action. As alpha B is changed, alpha A is also changed to satisfy the equation alpha A plus alpha B equal to 180 degree. Thereby you can bring a motor that is working in forward motoring into the reverse motoring operation by controlling the firing angle of these two rectifiers. Then the inductances L1 and L2, that is that will be causing, that's one disadvantage of this one. Inductance L1 and L2 increases the weight, volume, cost, and the reversal time of this, and the circulating current increases, losses, and the transient response is slow because of the increasing in the time constant. Therefore, it is not the time constant is 4 and it is not fast, and power factor and the efficiency are low because of the inductance in the circuit. Therefore, these are the disadvantage of simultaneous mode of control of a dual converter. Coming to the non-circulating current type dual converter, that's also called non-simultaneous mode of dual converter. In that one, only one converter is working at a time. And for example, in quadrant 1 operation, converter A is operated, alpha A is less than 90 degree as a rectifier. It is operated as a rectifier, and alpha A is made less than 90 degree. And the firing pulse to the converter B is blocked. We are giving the firing pulse only to the converter or the rectifier A. And to motor run at the forward direction, and in this case motor is running at forward direction. Now for speed reversal, in this case in non-simultaneous mode, for speed reversal, that is to make to work in the third quadrant here, the motor must initially operate in the second quadrant and then to the third quadrant. It has to bring from the first to the second and then to the third quadrant. For this, the operation must transfer from the converter A to the converter B. That is, current direction is to be reversed. That is, if you operate converter B, then the current direction that will be reversing in this direction, or the current through the armature is reversed, or that is made to work in this, current is made negative, that will be coming to the second quadrant. Before converter B is activated, all the thyristors in converter A must be turned off. It should be turned off. Otherwise, a line side short circuit of the converter B through the conducting thyristors of the converter A will be taking place. Therefore, before switching on B converter, A should be completely switched off. Otherwise, there will be a shorting of this between the lines. That should be avoided in the case of a non-simultaneous mode of control of dual converter. Continuing non-circulating current type of dual converter, armature current is forced to zero by increasing the firing angle of converter A. Therefore, when it is working from this first quadrant, it is brought to this one. First thing what we are doing is that you are increasing the firing angle and increasing the firing angle of the converter A. After zero current is sensed, at that time of 2 to 10 millisecond is provided to ensure the turn off all the thyristors in the converter. That time is provided. Then after that only we are giving the signals, switching signals to the converter B. Now the firing pulses are withdrawn from the converter A and that is given to the converter B. Therefore, when alpha B is more than 90 degree, armature voltage is positive and armature current is negative. That is working in the second quadrant. That is when alpha B is more than 90 degree. Here the voltage will be plus here and minus here, and with a positive voltage, and the current will be negative. So for that is made to work in the second quadrant. It is the forward regeneration. Now the speed reversal means it has to brought from the reverse motoring operation. Speed reversal is achieved by making alpha B less than 90 degree. If you make the firing angle of this one less than 90 degree, you'll be getting plus here and minus here, meaning that you are getting a negative voltage across the armature and the current will also be negative. Therefore, both voltage and currents are negative. That will be working in the third quadrant. That's what's called the reverse motoring. The product will be positive. That will be the rotation will be omega is negative. That is will be rotating in the reverse direction. What's called the reverse motoring. Speed reversal is achieved by making alpha B less than 90 degree. Both armature and voltage and currents are negative. That will be made to work in a third quadrant. And quadrant 4 operation, converter 1 is operated as an inverter. That is alpha is made more than 90 degree and the firing pulses to the converter B is blocked. Therefore, you can make by controlling this converter, you can make either in first quadrant or fourth quadrant. And by controlling this B converter, you can make either third quadrant, so second quadrant or third quadrant. Therefore, 4 quadrant operation is possible by using non-circulating current type of dual converter. Another thing is that in dual non-circulating current type, no inductance is required, but the same diagram is used. There is no circulating current in that case. There's no linking inductor is required in the case of a non-circulating current type. Coming to the advantage of non-circulating current type of dual converter, non-circulating or non-simultaneous or non-circulating current type control has the advantage of increased efficiency and power factor because of the absence of circulating current. Therefore, there is no circulating current. It does not need reactors, and hence the cost and weight, noise, and the power loss are very less. It provides quicker response compared to the other one to change the firing angle. Therefore, all the disadvantages in the circulating current mode is rectified in the case of a non-circulating current type of control of dual converter. Coming to the disadvantage of non-circulating current type dual converter, proper protection is necessary for avoiding the short circuit due to the multi-functions in both converters, because that is both converters are simultaneously operated. In that case, there will be a short circuit that should be avoided. That a delay time should be provided. A delay is required to shift the operation from one mode to the another mode. Therefore, advantage in non-circulating current control method provides faster response compared to the circulating current method. Let us see a problem. a 220 volt 1500 rpm 50 amperes separately excited DC motor has armature resistance of 0.5 ohms. Armature is fed from a 3-phase circulating current dual converter with line voltage of 165 volt, and determine the converter firing angles for the following operations, that is motoring operation at the rated torque and 1000 rpm, braking operation at the rated torque and 1000 rpm, and motoring operation at the rated torque and minus 1000 rpm, and braking operation at the rated torque and minus 1000 rpm. Actually, this is the first quadrant operation, this is the second quadrant operation, this is the third quadrant operation, and this is the fourth quadrant operation. Now let us see that one. At rated speed 1500 rpm, what is the back EMF? Back EMF is given by the voltage, supply voltage V minus IARA. The first is forward motoring at 1000 rpm, that is operating in the first quadrant. Now corresponding to 1000 rpm, already found that a rated speed that is at 1500 rpm, we found it as E equal to V minus IRA equal to, that is 195 volt. This is the back EMF corresponding to 1500. Now corresponding to 1000 rpm, you can find out the back EMF that's equal to 130 volt is the corresponding back EMF, that is 195 divided by 1500 into 1000. Now once you get this is the back EMF here, you can calculate to get this to get this much back EMF, what should be the voltage VA? VA equal to EA plus IA into RA. Therefore E, that is the back EMF, or the VA equal to E plus IA RA. The corresponding back EMF is calculated, that is this back EMF, that is E2 plus IARA. You are adding up these 130 plus IARA 50, that is the current is equal to 50 amperes and 0.5, and then that is equal to, it's equal to 3 VML by pi cos alpha. That is the average voltage across the armature in a 3-phase converter. It is equal to 3 VML by pi cos alpha A. Therefore 3 into VML, that is the root 2 times 165. 165 is the line voltage RMS value, maximum value equal to root 2 times 165 divided by pi into cos alpha A. And only in this equation, if you found this is the armature voltage, that is equated to 3 VML by cos alpha. The only unknown is alpha. Therefore the cos alpha is calculated, and 0.6956, and from that one you are calculating what is alpha A, 45.9 degrees, and alpha B is equal to 180 minus alpha A is equal to 134.1 degrees. This is the alpha A and alpha B corresponding to forward motoring operation at 1000 rpm, that is operating in the forward motoring region, first quadrant. Continuing the problem, second part is braking operation at 1000 rpm. Braking operation at 1000 rpm means it is working in the second quadrant, that is the second quadrant here. The corresponding equation now it is equal to armature voltage equal to the back EMF corresponding to 1000 rpm, that is E2 minus IA into RA. IA into RA, because the current is negative, second quadrant current is negative, that is why E2 minus IA into RA we will be getting, it is equal to 130 minus 50 into 0.5, and that should be equal to 3 VML by pi cos alpha A, and 3 into VML equal to root 2 into 165 divided by pi into cos alpha A. And equating this one, you will be getting cos alpha A equal to 0.471, or alpha A equal to 61.9 degrees, and alpha B equal to 180 minus 61.9, or equal to 118.1 degree. Therefore this is the alpha B, and this is alpha A corresponding to the braking at 1000 rpm. It's a second quadrant operation. The next one is motoring at minus 1000 rpm, that is operating in the reverse motoring quadrant or region. Therefore at corresponding to minus 1000 rpm, the back EMF is equal to, the magnitude will become, it is that's equal to here back EMF equal to 195 into minus 1000 divided by 1500. That's equal to minus 130 volt, or that's equal to minus E2. Whatever we are saying, that's equal to minus E2. And the corresponding in this region or third quadrant, corresponding armature voltage VA equal to, since the voltage and current both are negative, here voltage is negative and current is also negative, minus E2 minus IA into RA, or minus 130 minus 50 into 0.5, which is equal to again 3 VML by cos alpha A, equal to 3 into root 2 into 165 divided by cos alpha A. Only unknown is alpha A, where cos alpha A equal to minus 0.6956, or alpha A equal to 134.1 degree, and alpha B equal to 180 minus alpha A, which is equal to 45.9 degrees. This is the value of alpha A and alpha B corresponding to reverse motoring, that is in the third quadrant operation, third part of this one. And the last part is braking at minus 1000 RPM, that is working in the fourth quadrant. In that case, again you can say that corresponding armature voltage VA equal to, voltage is negative and current is positive, minus E2 plus IA into RA, or it is equal to minus 130 plus 50 into 0.5. That is equal to again 3 VML by cos alpha, 3 into root 2 into 165 divided by 5 cos alpha A, and from that one cos alpha A equal to minus 0.471, or alpha A equal to 118.1 degrees, and alpha 2 equal to 180 minus 118.1 degrees, or 61.9 degrees. This is the alpha B and this is the alpha A, in order to work the motor in the braking operation with a minus 1000 RPM, or to make it work in the fourth quadrant is called the forward regeneration.